kind of a theoretical part of calculus that's going to lend support to that method that we just used indirectly, but probably should be stated explicitly, optimization problems. Okay? So I mean, the business, of course, of translating the problem into mathematics is not really requires any theory. That is pure common sense. Okay, so it is when we get there, why does it work, and why this setting things equal to zero derivative gives us pretty much all we want. Well, it will need some support, but at this point, let's just put this in the form of a theorem, and it will be sufficient. Okay, so maximum minimum points, and as you can see, we have put it on the list. We put on the list the points where the derivative is equal to 0, and as well as the endpoints. Technically, there is a third possibility, so 0 derivative and the endpoints of the closed interval. But there is also a possibility of when the derivative is undefined. So just in case it is included, just in case. So a theorem is called global extreme points. As they are found through the derivative. So so we do assume that our function f is continuous on a closed bounded interval AB. So also suppose C is in AB is a global maximum or minimum point. Well, there are pretty much three possibilities. The first, f prime of C is 0. Number 2, f prime of C is undefined. And number 3, C is equal to A or C is equal to B. Okay? So as you have seen, we just every time we use this, we assume that the function was differentiable, but just for completeness sake, so we can handle a simple function as the absolute value. So it has only one questionable point, and we know that how to handle it. It just all it takes is just put it on the list. So if the function is not differentiable at one single point, that's not really that bad. We just enlarge the list by 1. Okay, so in this particular case, if I am to maximize, or let's say minimize, the absolute value function, all I have to do is say on -1, 2. Then what I do is I just include on the list. In this particular case, there isn't even the derivative equal to 0. It never is. So the list will be short the two endpoints and the point where the function is undefined. So -1, 0, 2, and these are the 3 points to be considered. And in what sense? Nothing. Just the list. Look at. We don't have to look at the infinitely many points anymore. We'll look at these values of these 3 x's give us 3 values of y, and these 3 values of y are to be compared. 3 values, that's all it takes, and then you'll know which one is the largest at the maximum, which is the smallest as the minimum, the end. Okay, so that's an example, and that is the idea behind it. Okay, so it also all follows from what we know about from Fermat's theorem, pretty much. Okay, however, we had another theorem, and that was the extreme value theorem. Why this works out to begin with is the extreme value theorem about continuous functions, and with continuous functions guarantees the extreme Value Theorem guarantees that the maximum is attained. It's not, you cannot have this. Okay, this is the biggest problem that you might encounter when you're trying to define a function, and then suddenly you have, if the function is discontinuous, then the maximum is not attained to begin with. So the question is not really about differentiability as much as about continuity, which is a looser restriction, but we still have to impose it, and that's why the condition number 1 is the continuity of the function. That way we can guarantee that at some point, at least we know that it is there somewhere, that point C, which is the local maximum or minimum point. Okay, so once again, the Fermat's theorem, which is kind of contained here, tells us that the extreme point produces zero derivative if the function is differentiable. Okay, so furthermore, we are talking about some more theory, and the theory is about what does the derivative tell us about the average rate of change. Okay, so that's the question. So the derivative itself, let's speak in terms of driving as the main metaphor. So then what we're talking about here is what the derivative, the substitute for the derivative is the velocity. So the question, what does the velocity tell us about the average velocity? So velocity, meaning instantaneous velocity, tells us about the average velocity, which is kind of the opposite of what we have been doing. So remember that the derivative was defined as the limit of the average rate of change. So f prime of c is equal to limit f of x minus c minus f of c, or x minus c, x goes to c. That's the definition. Okay, and once again, if you interpret this in terms of motion, then this is instantaneous velocity. In the meantime, the fraction is the average velocity. Wasn't there a problem on the test about average velocity? Oh, right, average rate of change. Right. Okay, yeah. So that's what we're talking about. That the data was given in the form of a table. Okay, and which is okay because that's frequently how you have it to begin with. But if we are moving on to more theoretical way of doing things and more accurate, then we take a limit. So that's the crucial part that really makes a difference. And but it is still that limit turns average velocity into instantaneous velocity, and then we're moving this way, right, from the average velocity to the instantaneous velocity as the interval over which the instantaneous velocity is evaluated getting shorter and shorter and shorter. Okay, so that's what we did. And now look at it. We are moving in the opposite direction. We are asking ourselves, what if we know the derivative? Does it tell us anything, if we know the velocity, does it tell us anything about the average velocity? Okay, and that's what we are gonna pursue. Okay, so if we set aside this for a moment and approach from a different direction. So the question is so suppose you're driving on a road, okay, and so you left home, okay, and then you drove for an hour, and then you came back, okay. So then so in an hour. Okay, so whatever happened, we don't know. Well, so maybe somebody was left at home and all they saw is you leaving home and then coming back. Okay, so that's the information that the person that stays home has. So you left and you drove, and the only thing that we know that you stick to this road, so you may have driven back and forth, but you didn't make any actual circles. So the question is, what do we know about the velocity? Instantaneous velocity. Of your driving. Or say, let's switch, and let's suppose you are at home and somebody you're living with left driving and then came back. What can you say about the instantaneous velocity during that period of time? The person may be driving fast, slow, and then fast again. But one thing is what?
It's inconsistent.
It is what?
Inconsistent. Inconsistent. Always changing.
It could be, but it doesn't have to. He could be driving for first half hour at the constant speed, and then for another one in the opposite direction. Well, the thing is that the person would have to stop. To come back, you have to stop, and stop means the velocity is zero. Okay, so it must have been zero. Somewhere, at some point, you don't know anything. Only you know that the person came back, and then you still can draw a conclusion, and the conclusion is velocity, instantaneous velocity was zero at some moment of time. Okay, so if you want to do graph, then this is your location, so this is time, and this is location. So then starting from point 0, this is what happened. You may have driven fast, then slow. You turned back, and then you came back. Okay, so assuming the function is differentiable, then, well, I guess my picture wasn't. I do want to assume that the function was differentiable. So you came back, maybe, and then you just wiggled around. But the point is that at some point your tangent line must have been horizontal, which indicates the time of that during that hour when you would drive, you stopped. Even though for a moment, it is possible that you may have stopped for a moment, no more than that. But that's what happens. Okay, so that's the kind of a common sense conclusion that we can make. Okay, so that takes the form of what we say, what we call Rolle's theorem. So we have a function that is once again continuous on an open interval, on a closed interval, AB, and then we require it to be differentiable on an open interval. Remember that there is always trouble with differentiability of a function on a closed interval. You can only do it one-sided. Well, same with continuity. The point is that we do not have to say anything about differentiability at the end point. So, and then we know that the beginning and the end, just like over there on the picture, is the same. Then there is a C in AB such that f prime of C is equal to 0. The picture captures that idea perfectly. So the proof is a little bit tricky, but it relies essentially on the Fermat's theorem, and so and extreme value theorem. So there is a maximum point somewhere, and which means that if the function is differentiable at that point, there is the derivative equal to 0. That's what Fermat theorem says. Okay. So we're not going to go into that. The picture is more or less. I hope it is convincing as it stands. But the Rolle's theorem is really never used directly. It is a stepping stone towards a bigger theorem that we really care about. But then to proceed in that direction is to see where is the average velocity. I've been talking about the comparison of the average velocity and the instantaneous velocity. Okay, so the instantaneous velocity we have here, it is derivative. It's the derivative. Instantaneous velocity, where is the average velocity? And what is so special about this picture is what is the average velocity here? What's the average velocity over this period of time? Oh, do you remember what the definition of the average velocity is? Same as average rate of change, difference quotient, all of those words are good. So what's the average velocity?
Will it be zero?
Yeah, it will be. That's right. So the definition is displacement over time. And displacement is zero. Look, we came back, right? So there you go. It will be zero over time, whatever that is, and it is zero. So, and that is that's the match. The match is, turns out, these are two numbers. The average velocity and the instantaneous velocity are the same. So that's what's behind the Rolle's theorem, is the match between, as I said, the average velocity that is known ahead of time. So this is the average velocity is right here pointed out that the displacement is zero, therefore the average velocity is zero. And then we discovered that at some point, according to the theorem, the instantaneous velocity is zero. So average velocity over extended periods of time, not from the limit, but over some fixed period of time, there is somewhere in the middle, with the same average velocity. So so that is a plan. The arrow points in this direction, so like this, from the average velocity to instantaneous velocity, okay, in that direction. And but the only problem with it is that it is zero. So it is very limiting. So this is limited to zero. Okay, so what about average velocity that is not zero? So let's try to figure out what that means. So do you see what I'm talking about?
Average velocity isn't zero.
Right. Yeah, but then that's the assumption. The conclusion should be also that you are at some instantaneous moment, your instantaneous velocity will be equal to that average velocity. Let me try to illustrate this with a picture that is modified picture from right at the top there. So the average velocity, suppose it's not zero, okay, which means that you have not come back to your home. You have driven somewhere and then did not come back. So maybe like this, okay. So and then you're here. I think it's like this graph. Okay, so this is your path, not path, but rather it is once again time against location. Okay, and this is the end of your drive, say 1 hour or whatever. Okay, so as you can see, you didn't come back, so the average velocity is not zero. What's the average velocity here? How do I find the average velocity?
You would draw a line from your starter to your end point and take the slope of that line?
That's right. It is. The definition still applies. It's displacement over time, and displacement is this. Right? So this is the displacement, and you divide by time, you have your average velocity. So still applies, and it is not equal to zero. Okay, now fine, and as you said, the average velocity is equal to the slope of this line, this very important line. Okay, so where is instantaneous velocity? At some moment, that's what we want to conclude, at some moment of time, your instantaneous velocity was equal to the average velocity. Can you conclude that and explain it graphically?
It would be at some point on the graph where the slope of
That's right. It is. The picture is very similar to this one. So we started with the average velocity equal to 0. So that was the line that connected the beginning with the end. Now we have a new beginning and the end, and when you have a new slope, so we're just looking for tangent lines, possibly having this slope rather than necessarily 0. So there's still a bunch of them. So how you'd find them might be slightly challenging, but you can imagine that you take like a ruler and you just put it on the slope into the bottom and then slide it parallel in such a way, and then until you hit it and you see the tangent line. So they have to have the same slope, and it is convincing, at least convincingly, we can conclude that there are some points with that property, just as we had it here. Okay, so and the theorem looks very similar to Rolle's theorem. The name is different. It's called the Mean Value Theorem, and so let me state it now. So I want to keep it close so that we see it's not really that different. The only part that changes is the part 3, and certainly the conclusion as well. So. Okay, so mean value theorem. So once again, we suppose the assumptions are almost the same, but this time there are only 2. So f is continuous on AB and differentiable inside of it. On the open interval. Okay, then there is a C, that part is the same in AB such that, and at this point we just have to be specific about that language, that with the language that we have used the word the language of slopes, as well as secant line. I didn't actually use the secant line, but it is definitely, this is a secant line, right? We could speak of secant and tangent lines, okay, but this time we want to rather speak of derivatives as well as well, so f prime. So look at the theorem over here. So Rolle's theorem. I have omitted condition 3, which is the restriction that produces the 0 average velocity, and so that has disappeared. But that last statement with this one has to be modified in order for us to have our identity straight. So f prime of C is equal to, and now on the right I wanna have the average rate of change, which is the slope of that secant line. So what is it? So if this is y equal f of x, right, and they say this is a and this is b, okay, what is the slope of that secant line? Rise over the run, right? So what is it? Right, yeah, that's right. So the locations will be f of b minus f of a divided by b minus a. Okay, so that's the theorem. It will be proven very convenient in the near future. But the one explanation is kind of semi-practical, but I just like it to bring it up because it's, once again, we continue with this analogy of instantaneous velocity, and that's the problem of speeding. Okay, so you can imagine the situation. I probably, one day I should check out the actual laws of speeding. But considering how the speeding is established, it is with the radar gun, right? So which means that they're measuring, strictly speaking, your instantaneous velocity. So then the law probably says that you're not supposed to have your velocity at that moment of time larger than 70 miles an hour, right? Okay, so that seems reasonable. So now, what if hypothetically you have one policeman sees you in Huntington and writes down your number in time, and then within 30 minutes, another policeman writes down your number in time in Charleston. Okay, what would you say to that? So 1 p.m. Huntington, 2 p.m. or 1:30 is what I said. 1:30 p.m. in Charleston. Okay.
So that you were going way too fast.
Yes, but how do you know? You see, can you conclude that your velocity actually exceeded 70 miles an hour at some point? Because there was nobody to witness it. Nobody saw it. The policeman saw you leave, and the other one saw you arrive. That's all. So that's all they can testify to. So can they still convict you of speeding?
By the law, they wouldn't be able to. But if it didn't matter.
They are allowed to infer. See, they are allowed to infer conclusions. So if they are supplied with this theorem, they could infer that your velocity was in fact above 70 miles an hour, which is, I'm not a lawyer, so I'm guessing that I think inference is a possibility. So of course the inference would have to be, not the policemen are not allowed to infer, or maybe they are, I am not sure, but it seems plausible. So the judge, say, making that decision would add 2 and 2 together, but you need the theorem. Okay, so because if you want to really rely on something other than just a common sense, you could argue common sense, but it's much better when you have a theorem in your hand, it says exactly that. So your average velocity was whatever, a lot miles an hour. Which means that at some moment of time you actually did speed, at some moment of time. What it was, it doesn't matter. And you just infer that. So even though nobody was there to witness it. So I'm not sure if it was tested ever in court, that kind of idea, but probably it may have. Probably relied on common sense. I do remember the story about somebody challenging the stop sign ticket because the cop says that he did not stop at the stop sign. Okay, and he argued that the cop was there was some obstruction right at the intersection, and he was making a turn, and therefore the policeman only was able to see the change of the angular velocity, not the linear velocity, and the linear velocity is what counts. That's what stopping is actually. That's when the linear velocity is 0, and the impression that you might get that there is no stopping because the angle is changing, continues to change almost at the same speed, even though linearly you have stopped. Okay, so that's a hard argument to make, but apparently he got away with it actually. Yeah. So and there is some paper somewhere where he wrote it up. Okay, so but the main application is, in addition to what we have already done, is not really to estimate that instantaneous velocity, but rather to estimate not estimate, but actually say something about the sign of what the sign of the derivative tells us about the monotonicity of a function. Okay, so just look at the equation that we have. So say I have my function is equal to x squared. Well, how about I take x cubed? X cubed, then f prime of x is 3x squared. What's so special about x squared? It's positive. Okay, so this thing is positive for all. Remember, we don't know what that c is, which is really mathematically very common, but otherwise is weird because you don't know where it is. We only know where that it's somewhere. Okay, so that's all the extent of information is available. But it's okay if we are in this situation that I'm looking at. The derivative is positive everywhere, or none other than 0. So the derivative is positive, which means that the left-hand side is positive, which means that the right-hand side is also positive. Okay, so f of b minus f of a, b minus a, will be larger than or equal to 0. Okay, so b is, we'll look at this one is positive, because that's how we chose a, b, or well, let's just choose b larger than a if we choose. Then we conclude that that f of b will be larger than or equal to f of a. That's called an increasing function. Okay, so that is really what we're after. So deriving monotonicity, as that word is, the collective word for decreasing or increasing behavior, is we derive it from the derivative. And once again, the establishing something that is the increasing behavior of a function without the derivative is quite a pain, because you have to compare pairwise every pair of points on the graph. You have to look at them and see which one is higher every time. So infinitely many, just like with solving optimization problems, hypothetically you have to compare infinitely many points. But here, if you know the sign of the derivative, that's all. If you know the sign of the derivative, then you know the monotonicity of the function, as long as the function is differentiable. So this is very quickly how we demonstrated that function x cubed is actually increasing without any plotting. And so it will be, indeed, at every single moment of time, it will be increasing. So, which confirms the graph. And the point, of course, is to be able to apply to functions that might not be as simple as this and not as easy to plot. Okay, so that's my x cubed. But we are not going this way. No, we're going the other way, like this. So we're using the derivative in order to understand the function. Okay, so certainly the derivative comes from the function to begin with, but sometimes we have information that is indirect. And so, for example, if we know the derivative, then we can say something about the function. Of course, the meaning of this is really simple in common sense. So what we're saying, well, let's go back to driving. So what we're saying here is, if the velocity, if we're driving forward, then we're moving forward. That's pretty much it. So if our velocity is positive, we're moving in the positive direction. That's the conclusion we're making. Okay, so it is a common sense conclusion. It just requires careful mathematical reasoning, which is we sort of had reviewed of. Okay, so let me put once again, this is in the precise terms because we want it to be precise, just as these theorems are precise. We want to now to formulate the idea of monotonicity as a precise term. So, okay, so definition. So function y equal f of x is increasing on interval I if f of x1 is less than or equal to f of x2 for all x1 less than or equal to x2. I have to make let me drop this one. Oops. Like this. So that is the strict inequalities is what I have in mind. So if the inputs are moving from smaller to larger, then so are the outputs. It is very easy to visualize. We have x1, x2 here, okay, on the x-axis, and then we're looking at the values of y's on the y-axis, and they have to be higher. So this is f of x1, and this is f of x2, and that is the inequality that we observe between them. Okay, so that is the increasing function, and decreasing naturally the opposite. Decreasing if f of x1 larger than f of x2 for all x1 less than x2. Okay, so otherwise it is the same. It is the same definition. the careful attention is to be paid to the fact that it's defined on an interval. Okay, so for example, the example that might trip you up, if we take our function 1x. So f of x is equal to 1x. This is the graph. Look at it. Look at, not a pretty picture, but you can see what's happening. The graph is going down. Definitely is going down. It's also going down here. So what's the conclusion then? What can we say about this function?
It's decreasing.
No, we cannot say it's decreasing. Once again, it has got to be decreasing on an interval. And if we say decreasing period, then we're implying that it is decreasing on the whole of its domain. And it does not. Look at I picked this point and I picked this point. Which one is higher? So x's are moving from left to right, but y's are going up. So it's not decreasing as far if we are allowed to do that. If we are allowed to skip through the gap in the domain, then we don't have a decreasing behavior. Okay, so that's why we're so careful about this definition. And then we would, if we do want to describe it properly, then we would say, how would we describe it?
Decreasing on intervals -infinity to 0.
That's right.
And then 0 to infinity.
That's right. And on separately 0, infinity, like plus infinity, like this. So that is the conclusion that we draw about it. Okay. Any gap in the domain actually might be a big problem every time. It's like function is broken into two and they have nothing to do with each other. Okay, so that is the definition, and now we can think about the challenge. First think about how important it is. The issue of whether or not a function is increasing or decreasing. It might be something very practical. It could be motion, it could be prices, it could be anything. So that's very early thing that you want to know about the function. Is it decreasing or increasing? And at the same time, if you try to not use any of the tools that we have had, then it is not an easy task. So if you take I started with x cubed, so f of x is equal to x cubed. So you have to look at and compare x1 less than x2. Then you have to conclude that x1 cubed larger than x2, the opposite, less than x2 cubed. Okay? And for every pair of x and y that you pick, you should be able to prove it. When a function is this simple, you can argue then, well, of course, cubed make a function. The larger the number is, the larger is its cube. Okay, you can make that argument. But imagine that instead of x squared, x cubed, you have, say, x cubed minus x squared. It's not as simple anymore, and then the function will change its behavior throughout the domain. Sometimes goes up and sometimes goes down. In fact, if we try to plot this function, we'll probably even don't have to plot it. Let's take the derivative, and we have 3x squared minus 2x. 2x. Okay. So then, so if I factor it, I have, what is it, 3x minus 2. So I have, in fact, two important points on the x-axis. There's 0 and 2/3. 0 and 2/3. That's where the derivative equal to 0. That is where the monotonicity changes, right? If you think about it. So it's a cubic function that goes, as we just discussed yesterday or earlier this week, it goes up, except it makes a wiggle in the middle. Okay, so then just from this information, we can already tell that, and remember that if it crosses the x-axis once, to come back, so it behaves like this roughly. Remember the limits. From the limits, you can establish this. And then now we know that this is where it crosses the, actually it crosses the x-axis here, but over here it just stops somewhere. It has a zero derivative and 0 tangent line, which means that it means that, what does it mean? Hold on a second. x. Increasing, decreasing, increasing, decreasing, and then so the only way for this thing to work out is this. No, hold on a second. Yeah, okay, like this. Okay, so the derivative changes its sign, which we still have to work out, but it was negative here, I'm sorry, positive here, negative there, and then it becomes, not here, but rather over here it's negative, okay, then it becomes positive again. Okay, so that just the signs of the derivative will tell us the behavior of the function, and it changes its sign. Where does the function change its sign? And wherever it is equal to 0, and it is equal to 0 at these two values, 0 and 2/3. Okay, so you don't have to go into minute details of how this function operates and try to figure out whenever the monotonicity changes, and try to figure out what the x cubed is, which is supposed to be increasing by itself, but then x squared is also increasing, and you subtract two increasing functions. Do I get an increasing function? It's unclear. So you don't really want to go there. This kind of a comparison that works out for simple functions than anything slightly more complicated than that, and we are lost pretty much. But with derivatives, sometimes, at least for polynomials, for sure, we can solve these problems in a snap. Okay, so which is almost what it just did. So let me state the theorem that we're going to be using, and that is the well, just monotonicity theorem. Once again, there must be restrictions on the function. The function has to be differentiable. So suppose f is differentiable on AB. Well, just the interval, open interval. I. Okay, and then if f prime of x is larger than or equal to 0, no, let's say strictly larger than 0 for all x, in I, then f is increasing. Once again, increasing on that interval. So every interval, so the function is defined on that interval, and the derivative is defined, and we are treating functions separately on separate intervals. So, and then the opposite, naturally, if the derivative is negative for all x in I, the function is decreasing. Okay, so that is the theorem. How do we know? I just explained to you that all we need to do is to look at the mean value theorem. Okay, so compare, if we are to compare, well, case 1, say case 1, and I have x1, x2, x1 is less than x2, what do? I need to compare f of x1 and f of x2 with, okay, let me put it this way, less than x2. So I am within my interval. I don't know anything about this function. This is my interval I, and I picked two random numbers within this interval, x1 and x2, and now I have to demonstrate that the values of the function will be like this. So it will be higher in the second point and then in the first. So what do? Well, I form an interval. I form an interval like this in order to apply the mean value theorem. Okay, so these 2 points to be compared are in fact the endpoints of my interval. Okay, so this is what I have then. I have by the mean value theorem, which is satisfied, right? We have differentiability and continuity and everything we want. So I have what is it? F of x2 minus f of x1 over x2 minus x1. That is the average rate of change over that interval, right? And it is equal to the derivative of the function somewhere in the middle. Okay, so that's what the mean value theorem says. There is a c within that interval, so is some number between x1 and x2. Okay? And that pretty much does it, because the assumption is that the derivative of the function was all positive. So this one is positive. And then we're done. So f of x2 minus f of x1 larger than 0. So f of x2 is larger than f of x1, and we have our picture. Okay? So it is a roundabout way, indirect proof through something that is, as they put it sometimes, existential, meaning that something that exists somewhere, and even though we don't know where it is. And then it helps us to draw conclusions that are very specific, as you can see. And I just applied to x cubed, and I could do it with other functions as well, or any functions that I can handle. As long as I can compute the derivative, I can do it. So if I take my function, say sine x, I can explore its monotonicity very easily by exploring the sign of its derivative. Okay, so to determine the monotonicity of f, consider the sign of f prime. So monotonicity, complex idea that is done point by point, compared with a pair of points compared, like that picture over there. And it's replaced with something that is much simpler. The sign. So positive, negative, that's all. Okay, so well, let's do it. So I just take my f prime x, which is cosine x, and all I need to know about cosine is where it's positive, where it's negative. Okay, so I could either plot it, or I can look at my unit circle here to see what the cosine is, the projection on the x-axis. So if this is x, then where is cosine? This is cosine. This is cosine x. So as long as my x is not past the y-axis, right? So this shows the positive value of x. This is negative value of x, well, negative value of cosine. So if my x is this, then it has a negative value of x. Okay, so this is also cosine x. But as you can see, you can have either sign positive or negative depending on the angle. So let me point that out. In fact, so like this. So here positive cosine. So if these are x's, then cosine x here is positive. In the meantime, these, I put it in blue, these angles, cosine x is negative. Okay, so that's all we need to know. That's all we need to know is the angle. As you can see, the x is the angle. So as you can see, it changes from what's the angle at the bottom down is negative pi over 2. This is the angle, the angle down. This is angle negative pi over 2, and up this is pi over 2. So from negative 90 degrees to 90 degrees, that is the span of positive values of cosine, and then it becomes negative, and positive and negative, and so on. So you explore the whole thing, or you just say so cosine x positive for x between negative pi over 2 and pi over 2. So sine x is increasing on the interval negative pi over 2, pi over 2. Okay? Something we could have established in a different way, but this is really how it works whenever you want to analyze the function, which might be more complicated than this. Right now we're just confirming that what we already know can be established in this manner with the derivative. So let me pick a function that is more complicated. So well, let me do one more example before I do it. The exponential function. So once again, we're confirming the facts that we already know, and how easy it is to see the features of the graph that come from plotting them. Okay, so f prime of x is equal to e to the x, positive, so exponential function is increasing. The end. That was quick. So all you need to know is the exponential function is positive. Its derivative is the function itself, so the function is increasing. And this time I do mean that it is increasing. Increasing on the whole domain, between negative infinity, infinity. Okay, so the pictures that we saw, they now have been confirmed. So like this, right? So it's growing, even though it starts slow and then grows faster and faster and faster. And so there are no dips, there are no gaps. The function will keep growing. So that is just to confirm something that we already know, and the functions are simple and familiar. It is when the functions are new, made of old functions in some complex way, that is this method really shines. And so let's start on that, down that road. Well, let me do this function that we already saw. Well, no, not exactly what we saw. F of x is equal to x cubed minus 3x. Okay, so suppose that we don't know anything about this function, and we just we'll be looking at nothing but the derivative. Even though, you know, derivative frequently comes second. The first question to ask about the function is the domain, for example. So fortunately, this is a polynomial, so the domain is everything. Second question within the same, it's still first question, I'd say, x-intercepts. Okay, so that will be very helpful if we're trying to understand what the graph looks like without actually plotting it. So then x-intercepts, where x-intercepts, I probably shouldn't be too hard. X squared minus 3, so it is actually equal to x-intercepts are, what are x-intercepts? 0 and the second factor, plus or minus square root of 3, yes. So there are 3 x-intercepts, and that is sort of like what we would have accomplished with the pre-calculus analysis. Okay, so it crosses the graph in this fashion, in these 3 points. Now we're progressing to the next level, and what's the next level is the derivative. Okay, so level 1, derivative. So I compute the derivative, and then all I have to do is to look at its sign. 3x squared minus 3, it is fairly simple. So, but specifically what we're supposed to find out, in order to explore the monotonicity of the original function, I have to determine the sign of f prime of x. So depending on x, we need to establish what the f prime of x is, positive or negative. Well, so in other words, what it means is solve the inequality. We're solving inequality 3x squared minus 3 larger than or equal to 0, less than or equal to 0, so like that. So we need both. Okay, so we need to find all x's for which the function is negative and all x's for which it is positive. Okay, that's what it means to solve an inequality. Okay, so it is actually quite awkward idea and procedure for solving inequality. It is much easier to instead solve the equation and then see what it tells us about the inequalities, because actually 2 inequalities here. So instead, solve the equation. 3x squared minus 3 is equal to 0. That's not too complicated, right? So I have x squared minus 1 equal to 0, x is equal to x squared plus is equal to 1, and x is equal to plus or minus 1, right? Okay, so these are the cutoff points between the positive and negative. That's pretty much what we're doing here. And then it's really not that complicated, but it just needs to be done. So this is how you could just put an x-axis here, draw the two cutoff points, and we are now strictly speaking about the derivative only. So forget about the original function. We are looking at the derivative period. So whatever you see is what we care about. So the 2 points are -1 and 1. Okay, so I'm trying to plot the rough sketch of the derivative. I don't need a lot about it. All I need to know about this function is where it's positive, where it's negative. Okay, so what I have established is that it is 0 here and 0 there. You can say that these are two where it crosses the x-axis. Okay, so can you figure out what else we know about the derivative? We were looking for signs, so we only know 2 zeros. Well, we'll look at the thing about the continuous functions is that if you found the x-intercepts, which is what we just did, it means that the sign is, there are no others, and the function cannot change its sign without crossing the x-axis. So which means that within these 3 intervals, the signs are unchanging. Okay, so unchanging signs within these 3 intervals. So all we need to do is to determine what sign that is. So can you guess what they are? Well, there are several ways. Yeah?
Positive, negative, positive.
Positive. How do you know?
Because x for any number 1 or greater will yield the -3 relevant.
Yeah. Yeah. So wait. Did you factor it then?
And we just plugged in numbers.
Okay. So the method one is test or sample. Because, as I said, it does not change its sign, so you pick one number and it will tell you the sign, right? So, for example, I pick 0, for example, which gives me negative, right? Here I pick -2 to test, to sample, and -2 will give me 12 minus 3, so there you go, it's positive. Same thing, I pick 2 here, and it gives me the positive sign. I don't need the exact value, all I need to know is the sign. So testing, sampling is a good method. Another method is factoring. And this one is easy to factor. It is, so it's x minus 1, x plus 1. Okay, so the point being, it is especially good when there are a bunch of those factors. So instead of looking at the derivative, I look at the factors. Okay, so I could actually start from scratch, and what I know is I'm looking at the signs of each of the factors. So x minus 1, it is a linear factor, so it's very easy to actually establish what's happening to it. It will be 0 at 1, and then it's straight line, so it starts negative and becomes positive, right? Now we take the other one, x plus 1, it is 0 at -1, and otherwise it's still the same. It's first negative and then becomes positive. Okay? Now I put these two together. So f prime of x is the product of these. So what are the signs? Negative times, I'm going vertically. Negative times negative is positive. Negative times positive is negative. And then positive times positive is positive, with zeros here. Okay, so I get the same result naturally. Okay, and then with this data, which is certainly could be more complicated if you have say a polynomial has a higher degree than that, then there will be more factors, and there could be rational functions as well. So there are denominators to look at as well. So there will be more and more of those, but this is the basic ideas here. So we just look at the derivative. We found the signs. Now this is what I do, and now I'm indicating what's happening to the function itself. Increasing, decreasing, increasing. Okay, and just these arrows. This is the standard way of presenting this behavior or notation for this behavior, taken together, you already have this is already a sketch of the graph, right? You can just say this is it. So I could just do it this roughly. Okay, so and that is the like a degree 1 analysis of a function which relies on the derivative, and not much beyond it. So determining the increasing decreasing behavior, and that's pretty much how it works. Okay, so the only thing that might be more complicated in the near future is there might be not only there might be gaps. So if you're talking about rational functions, remember division by 0, and there might be you would have to be careful to look at those cutoff points. Some of them will be undefined, and then then you cannot connect them through those points. Such as, if you want to see that one again, is 1 over x. F of x is equal to 1 over x, right? Then its derivative is f prime of x is equal to negative 1 over x squared, which is negative. So then, carefully not drawing a conclusion that is wrong, it is negative, but really for every x, that is not equal to 0, which means that we have to split into 2, and there will be 2 splits. Let me do this again this way. 1 over x, that's the function, and it has 2. You still have to put a hole here at 0, and then say this is negative and this is positive. Okay, so that is my derivative, and then I do the same as we just did. I'll say this is nope. This one's still negative, right? These are still negative ones. Okay, so this will be my conclusion about the function. Decreasing, decreasing. Not one decreasing, not two decreasing for each of the two intervals. So then I will not try to do what I did over there and connect them into one curve. There is no one curve. There's a gap here. So I could, I don't know what the good way to do it, like suggest that there's a gap in the domain of the original function as well as the derivative. So best I can tell is that we have something like this. Maybe. The problem is that shortly to be addressed is why not like this, like that. Okay, so the difference between these two is the next topic. So it appears to be decreasing on both of the intervals, but in a different manner, right? If you look at these two, the manner the function decreases on the left is. Do you see it? How different is what's happening to the right? Right? You see it? It's called what? No, they are kind of mirror images of each other. Yes, but what I meant is what's happening to the slopes. What's happening to the slope on the left versus what's to the right?
One's decreasing, one's increasing.
That's right, slopes decreasing, and here slopes increasing. So what are we going to be talking about then? Increasing, decreasing of the slopes. What it's about? The slopes themselves are the derivative. We just did it, right? So this is f prime. So the slopes are the derivative, and now we're talking about the slopes decreasing. So what is we going to be using?
Change in slope.
Yeah. Okay. So you see what we just been doing. We're studying the change of functions through studying its derivative. Okay, but now we're looking at the change of slopes, which is a derivative itself. So we'll be looking at what? The derivative of the derivative. Okay, so the second derivative. So that's to distinguish between these two behaviors, we're going to need the second derivative f double prime. Okay? So in other words, to describe these are this is called concavity. How the an extra next level analysis which gives you the not only increasing decreasing behavior but also whatever has happening to the slopes, and you're going to need the second derivative, which remember in terms of this metaphor or analogy with motion, second derivative is what? Acceleration. That is the parabola. That's why you have a parabola, because y is going like this, because the acceleration is negative. Negative acceleration gives you, like similar to what's over there, the slopes are what? What's happening to the slopes? They're decreasing. They're decreasing, so the slopes are decreasing, which means that yes, the second derivative is negative, or as we know, in other words, the acceleration is negative. Okay, so that is the next topic, but it is a bit. I don't want to jump too quickly to that next topic, because this needs to be to sink in using just the derivative, using the derivative to study the monotonicity period, and then you use that understanding, you apply to derivative. So you use derivative to study the derivative, which means that you're using the second derivative to study it. Okay, but it is one step at a time. It's just kind of a self-referential idea. So you use derivative to study the function, but then the derivative becomes the function to be studied, and then you use its derivative, which is the second derivative. Okay, so okay, I guess we'll just pause until next week, and we'll do a few more examples of this before we get to the second derivative. Okay.